So 8.5, solving exponential equations and logarithmic equations. On the surface, these look worse than they are, in my opinion, anyways. But there's a lot of stuff that we've been doing already where we're just really trying to find same bases. So if we can force a base to be the same, then we get to pretty much ignore the bases and then just solve for the exponents, which is great, because then it's just a matter of saying, well, really all we're trying to do is make the exponents match, because if the base is the same and the exponents match, then we should get true equations out of those. But the other piece of good news is this is the last lesson for this class, the final one. There's no other new information that we'll be seeing after this for this class. So the uniqueness of b to the power of x, and we know that b is a base, that's why it's called same bases. So in an equation, if we can, again, get these bases to be the same, like this base 5, this is 625, we can get those bases to be the same, then we can solve for x pretty quick. And we don't necessarily need a logarithm. A logarithm could work in this case. You could use a logarithm to solve this one if you know how to use logarithms. But also, if we can get the bases to be the same, then it works as well. So for example, what we do is we say let's start with this one right here. We got 625 equals 5 to the power of x. Now, since I have a base 5, which is prime, by the way, this is important as well. If this was like base 10 right here, I would still try to find base 10s out of this value right here. But since it's base, but you could also say, well, maybe you're looking for base 2s or 5s, and so you have to look at the factors of some of those values. But if the base is prime like this one, then it's a pretty clear indicator that we're looking for base 5 factors of 625 in this case. So here's what I mean by that. So over here, I've got base 5 to the power of x. So that means I'm going to take 625, and I would like to just continually divide it by 5 to see what other values I get. Now, if I can continually divide these by 5, then I will have a base 5 expression on the right side of that equation. So I'd say, well, 625 divided by 5, that would be 125. Okay, and then again, this is divisible by 5 because of the 5 in the ones place value. So I'd say, well, let's divide that by 5, and that would be 25. And then 25 divided by 5 is 5 times 5. Okay, so we get all multiples, all factors of 5 right here, which means 5 times 5 times 5 times 5 is 625. And now we can write this as 5 to the power of 4. But it would equal the other side of that, which was 5 to the power of x. So like I've been saying is, welcome. Once we get these bases to match like we have right here, then the great news is that we get to ignore the bases. So at this point we say, let's take those bases since they match, and then let's just compare the exponents, because this means at this point, if I can get these exponents to match, then my base to that same power it should equal the same thing, right? So let's ignore those bases. Now I've got x equals 4. And like we've seen, sometimes this could be like x minus 3, 2x plus 5, and then you would solve that. So you may get fractional values out of these, but for now this one looks pretty good. And so we say, well, x is 4. So that means 5 to the power of 4 equals 5 to the power of 4. Yeah, because both of these would end up being 625. And like I said, if you had changed this into a logarithm, this would have been log base 5 of 625. You could have solved that and then gotten x equals 4 as well. Now this next one, 4 to the power of x equals 8. 4 is not prime, because again, we want to look at the base first. Now 8 is divisible by 4, that's true. So you could say, well, 8 is divisible by 4, and that's true. 4 would be the value we're looking for, but the other factor is 2. So the problem with this is that you can't say that this is 4 to some power, right? We don't know what this exponent is. So a base 4 is not going to work for us, which means that we have to change not just the base for the 8 that we're looking for, but also the 4. So you have to notice that if you look at some of these problems, sometimes the base, like you can divide this value, this product, by that base, but it won't go in. It won't factor very well like this one did, right? We just divided by 5, and it worked out pretty. But over here, we're dividing by 4, not very good, right? So we need to, let's get rid of that garbage. And let's change the base, okay? So you can change the base, yeah. Like we talked about in the last couple lessons, is a lot of this stuff really is changing the way things look without changing the value. So I'm gonna take 4 right there, my base, and I'm going to change the base, meaning I'd like to find a factor of 4. Maybe that can repeatedly multiply by itself. So that'd be 2. All right, so that 4 actually is 2 to the power of 2, and then that would be to the power of x. Okay, now this we would say is equal to 8, which we'll get to. And in fact, I'll use a exponent rule here. Since we got 2 to the power of 2 to the power of x, we can just multiply those exponents. So it's really 2 to the power of 2 times x. Now this equals 8, but I'm going to take the 8. Let's take the 8. I'm going to move it over here so I have some space to work with. But let's take the 8. Now I'm looking for base 2's, right? So that means I'm looking to divide the 8 by 2, which we know can happen. 8 divided by 2, that'd be 4, just like we've seen. And then 4 divided by 2 is 2 and 2. So 8 really, instead of showing it as an 8, again, this does not change the value, but it does change the way that it looks. It's now showing 2 to the power of 3. Well, is that okay? It is. We didn't, again, none of this changes any values. 2 to the power of 2 is still 4, 2 to the power of 3 is 8, and we still have that exponent of x as well. So now that the bases match, well, let's just compare the exponents of 2x and 3, because if we could get these two exponents to match, then we should have a solution. So I'll use the principle of equality here. Let's divide both sides by 2, and now I see that x, if it were 3 halves or 1.5, then I should get a true statement. Now you can go back over here, just do 4 to the power of 3 over 2, and yeah, you will get 8 if you put that in there. So this means I have found the solution. Now, this is called the uniqueness of b to the power of x, the same basis. Because, like we've seen, this one worked out very nicely. When we did some division for some factors of 625, we got base 5s out of that. But sometimes it may not work so pretty like this one, and you may have to determine what other base can you use in order to get the bases to match. All right, so a problem like this one, let's make this bigger. I have a base 10 to the power of x, no problem. I can take 1,000 here, and I know I can divide that by 10. So if I divide that by 10, that'd be 10 times 100, and 10 is the factor that I'm looking for because my base for my exponential expression is 10. So the 100 as well, let's divide that by 10, and of course that's 10 times 10. So this one is one of those pretty ones, right? Where we say, instead of 1,000, I'm going to show this as 10 to the power of 3. 1, 2, 3 10s multiplied together. And then this would equal the other side of the equation, 10 to the power of x. So we have forced these two exponents, the two bases to match. So we can now ignore the bases because we are solving for a variable, an unknown, and now we can compare just the exponents. So in other words, what I have here, x equals 3, that's comparing just the exponents, because if we can get these to match, then you have 10 to the same power. So yeah, x, if you could replace that with 3, even back here, 10 to the power of 3, boom, you'll get 1,000. That's it. So this one, the base comes already matching, right? Base 2 to the power of x minus 3 equals base 2 to the power of 3x plus 9. And so, at this point, we get to ignore the bases, meaning that all we're doing is comparing the exponents. So x minus 3, if I could get it to equal 3x plus 9, then I will have the correct value of x to force those exponents to match, right? Because then you have 2 to the same power for both sides of that equation. Well, this is just a regular old-fashioned equation, which should warm our hearts because we haven't seen these in so long. Should bring it back some nostalgia, right? So I'm going to put the x's on the right and the numbers on the left. Some students like to put them on the x's on the left, numbers on the right. Doesn't matter. The reason why I'm putting the x's on the right is because I want my coefficient to be positive. Trying to keep it positive, you know, glass half full. Yeah, there we go. So this means my 1x right here, and there's a phantom 1 coefficient, is on the number side of things. Well, we don't want x's on the number side there, so I'm going to subtract 1x from both sides. Additionally, at this point, see how we got the x's on the right side, but we got a constant, the positive 9 on the right. As it turns out, I can also get rid of that right now, so minus 9. So the purpose of this, just getting x's and numbers on the correct side, is just a matter of zeroing out values. So 1x minus 1x, that zeroes out. Negative 3 minus 9 would be negative 12. And then this would equal 3x's minus 1x's would be 2x's. And then, yeah, we got the 9 minus 9, which also zeroes that out. So that goes back to principles of equality. We wanted to force those to zero out. But the last thing I want here is a coefficient of x. That's a 1. So how do you make a 2 coefficient of 1? Just divide it by itself. So 2 divided by 2 is 1. By the way, crossing it out like this, that's a 1. It's not just that it's crossed out or canceled. It's actually a phantom 1. And then we get a negative 12 divided by 2, which is negative 6. So this means you could type this into the calculator, right? 2 to the power of negative 6 minus 3. It's going to be some pretty ugly fraction or decimal. And then if you type in 2 to the power of 3 to the times negative 6 plus 9, as it turns out, you will get the same exact value on both sides there. So we did find the solution. X equals negative 6. It's done. 16 to the power of x minus 5 equals 4 to the power of x minus 3. So the bases do not match. We need them to match before we just start comparing the exponents. So we're going to force them to. And I tend to look at the smaller ones, right, because I can't just take this 4 and make it a 16 without it affecting both sides. But I can take a 16 and make it a 4 without it affecting both sides. I mean, I don't need a principle of equality to make a 16 base a 4 base. Now, some students even would use a base 2 on this one because you could. Both 16 and 4 are, you can find factors of 2 that make that match nice. But if I can get these to match as is, then it's going to make this, in my opinion, a lot easier. So the 16, like I said, I'd like it to be a base 4. 16 by itself is 4 times 4, right? So that shows that it turns out very nice. It's 4 times 4. If I got like 4 times 3 right there, okay, then I've got to find a different base to use. But this one works out nice. So the 16, just the 16 base right there, I'm going to show it as 4 to the power of 2, shown in parentheses. And that would have been to the power of x minus 5. And then this just equals the other side of the equation. So that equals 4 to the power of x minus 3. Okay, now with the exponent, I've got 4 to the power of 2, and then on the outside of the parentheses, I've got x minus 5. By the exponent rules, this means that I would have to distribute the 2. In fact, there's a couple different directions we can go. Right now, you can ignore the bases as long as you understand this exponent rule right here. In my mind, I was going to just distribute the 2, but it doesn't matter which direction you go. You can get rid of the 4s now, you can distribute the 2, keep the base 4s, and then get rid of them after that. Doesn't matter, you're going to get the same answer. All right, it has been decided. Let's get rid of the bases now. So on the left side, okay, we're just going to compare the exponents. I have 2, and in parentheses, right, we got the x minus 5. And then this equals 4 to the power of, we got rid of the base, right? So it's just x minus 3 now. This is an equation. We just got to solve this equation. And like we would with any equation, distribution first, then combine like terms if it's necessary. It's not in this case, but if you needed to, then you would. Distribution, combine like terms, isolate your x's with principles of equality, and then force your coefficient to be 1. This one's going to turn out pretty nice. So let's start by distributing the 2 there. So that would be 2 times x, which is 2x. 2 times negative 5, which would be negative 10. And no distribution on the right side there. So this is my equation, and now I will isolate my x's. This time I will put the x's on the left, numbers on the right, because it doesn't matter which side you choose. But this means that the 2x in green is on the correct side. It's on the x side of things, but the negative 10 constant, got to zero that out. So I'm going to add 10, but it's a principle of equality. So if I do it to one side, I need to make sure to do it to the other side. So that zeroes out. That's nice. Negative 3 plus 10 is positive 7. And I see also this x right here is on the number side of things, so I'm going to get rid of that. And by get rid of, I mean zero out. So I'm going to, that's a 1x, by the way. I'm going to subtract 1x from both sides. So 2x's minus 1x's is 1x's. And this would equal that positive 7 right there. Well, the coefficient of x, it's already a positive 1. So I don't need to force that coefficient of x to be a positive 1. It just stays like this. Now this means, again, let's go back. Okay, so up here at the top, I would like to check for truthfulness. So I'm going to put a question mark above the equal sign. And let's see, 16 to the power of, we have 7 minus 5. Enter. I got 256 on the left. Okay, well, what about 4 to the power of 7 minus 3? Enter. 256. So you see this, it forces the original equation to be true. And so that way we know we actually have found the solution. There is some thinking that's involved with this, right? I mean, you got to think, what base am I going to use? And will base 4 work? Because, you know, if this, yeah, right? Then you that wouldn't work. Like, yeah, if this base was 8, no good. Or if 16 was 32, no good, right? I mean, 32 is divisible by 4, but it'd be, you'd end up with another factor of 2, so that wouldn't work either. So you may have to change the bases yourself. Again, you may have to change both bases, but we only had to do one in this case, and I think that's pretty good. All right, so yeah, this one, I think it looks ugly too. I think it looks ugly though, not just because of the exponent, but because you have a fraction, and a fraction to an exponent makes things ugly, right? But in fact, this is not so bad, because what we would like to do is not have a fraction. I think that's in almost everyone's minds. If we could just get rid of that fraction, we could feel good in our hearts. Not about just math, but about life in general, because fractions destroy lives. They've destroyed many lives, which we don't want it to destroy your life, okay? So let's get rid of this fraction. How are we going to do that? Well, if you get a fraction, the first thing I would do is I would like to flip it. That's reciprocated. And this goes back to exponent rules. That 1 over 3, if I flip it to 3 over 1, all it does is it takes that exponent of x and it makes it negative. Okay, now 3 over 1 as well is a nice value to work with because it's dividing by 1. And so really, I'm just going to show this as base 3 to the power of negative x. Now this still equals 81, right? And if we had started with something like this, I don't think a lot of students are so bent out of shape about the negative exponent. Like, that's not the problem. But the base being a fraction, yeah, it's nasty. But we did it. We got rid of it, right? All we did is change the format, by the way. We have not actually changed the value. This overall value of this equation is exactly the same as the original equation. We forced it to do what we wanted it to do, and I think that's extraordinarily powerful. But 81, right? So I'd like 81. 3 is a prime, so I'm not having to worry about any other factors of 81. But 81, I know it should be divisible by 3, at least if this works out nicely. Otherwise, we'd have to use a logarithm. But I got base 3. So 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. So you see, this did work out nicely, just like we kind of anticipated. 81, in fact, is actually 3 to the power of 4. So this is going to equal, I'm gonna change this a little bit. It's base 3 to the power of negative x. I just got rid of the parentheses. Hopefully that's okay. But again, the great news at this point is that the bases do match. So now all I got to do is compare the exponents. So negative x equals 4. And by doing this, this will have forced the expressions to match on both sides of the equal sign. Some students, by the way, they'll stop right here. They'll say, oh, negative x equals 4. Yes, that was so awesome. And they've done so much work, and they're so close. But you don't want a negative x. You want a 1x, just a phantom 1x. Right now, it's a negative 1x. In fact, I'll show the phantom 1. Let's get rid of that garbage. So let's divide both sides by negative 1. There's a principle of equality, by the way. So divide that by negative 1. Anything divided by itself is a phantom 1. So you end up with 1x. I'm going to show that as a phantom 1x. X equals 4 divided by negative 1 is negative 4. Now, again, just go back, do in parentheses 1/3 to the power of negative 4, and see if it is 81. It is. It's 81. So that means that when we replace the x with a negative 4, we get a true statement out of the equation. Now we know we actually have found the solution to the equation. So 1/10 to the power of x minus 10 equals 10 to the power of 4x minus 8. The good news here is that it's always nice to see a numerator that's 1 with the fractions, because that means I can just flip this. And the denominator already matches the other base. So again, I'm looking at this from the beginning, noticing that things should turn out pretty nice. Not everyone may be able to do that right now because it takes some experience, but this is going to turn out nice. Well, whether you notice that or not, you should notice that you have a fraction, and we don't want that fraction, right? So I'm going to flip that fraction. I'm going to make it 10 over 1. But in doing so, that's going to make this x minus 10. Now it's all of it, so I'm going to put this in parentheses, but by flipping it, it makes it negative. Okay, just like we saw in that last problem. And instead of showing this as 10 over 1, I'm just going to show it as 10. Okay, and in fact, you know what I'll do is let's distribute that negative 1. So that'd be negative 1 times x, which would be negative x. And then negative 1 times negative 10 would be positive 10. So I'm kind of combining steps right here. I hope that's okay. If it's not, you got to let me know. But this is going to equal base 10 to the power of 4x minus 8. And after all of that work that we just did, we have forced on our own, by our own will, to make those bases match. So we can compare only the exponents. So we got negative x plus 10 equals 4x minus 8. And this becomes an equation for us to solve. And we love solving equations because they take us back. And so, what the heck, I'll put the x's on the left and numbers on the right, just to show you it doesn't matter again. I'm going to show this as a negative 1x, but the 10, positive 10 in purple right there, it's on the x side of things, so I'm going to have to zero that out. So minus 10 from both sides, that will zero that out. But also the 4x is on the number side of things, so I don't want x's on that side, so I'm going to zero that out by subtracting 4x's. So now I have negative 1x minus 4x's, which would be negative 5x's. And this equals I guess we zeroed that part out, right? But negative 8 minus 10 is negative 18. And the last thing I got to do is force this coefficient of x to be a 1. And to do that, I'll just take the coefficient and just divide it by itself. So negative 5 divided by negative 5 is 1. 1x, phantom 1x, equals negative 18 divided by 5 is actually positive 18/5. I believe on the assignment it wants the fractional values. Like this decimal's not too bad, right? 3.6, I believe. But the fraction, in my opinion, looks better, which is weird because fractions destroy lives. Now again, if you go back up here to the top and you replace the x's in this equation with 18/5, you get a true statement. I don't know what it is, but you will get a true statement out of that, and it would confirm that you have in fact found the solution. All right, so again, this one, I don't think this one looks as nasty as one with a fraction. I'm not saying you won't see fractions in problems like this, but it really isn't as bad as it looks, okay? Just like we've been doing, hopefully you've noticed that all the problems that we've solved to this point have just the base and the exponent on one side, and it equals a value by itself. So here I've got my base and an exponent. I have something that's still multiplied by it, and I also have something added to it. I need to get rid of that stuff. Okay, so that means that right now I'm going to use principles of equality. I may have to use some even at the end, but right now I got to get rid of that garbage. So let's get rid of it. And by get rid of, to start, I'm going to make things 0. Now, I've got my base and my exponent on the left side. I'm just going to keep it there, okay, because we're looking at principles of equality. I want to get rid of that 31 to zero that out, so minus 31. This would be considered isolating the variable, which means the variable, you want it to be its own term all by itself. Okay, so 31 minus 31, that does 0 out. We now have 2 times 2 to the power of n, and this would equal 159 minus 31. Thank you. Boom, 128. And again, if we had started with just this part, we would have been like, hey, that's pretty cool right there. I think we could solve that. Maybe we could, maybe we couldn't. If we can't, let's continue. Well, even if you can, let's continue. I don't want anything multiplied by my base and my exponent either. So this 2 right here, I don't care that it matches the base 2. It does mean something, and you can do something with that right now. But for me, I want to get rid of that 2. I'm going to call it a coefficient, in fact. So right now, I'm going to get rid of that 2. Since it's being multiplied, that means I need to make it a phantom 1. So I've got to make that 2 a 1. How do I make a 2 a 1? Divided by 2. But if you do it to one side, it is still a principle of equality. You got to do it to the other side. So 2 divided by 2 is 1. Now I've got base 2 to the power of n equals 128 divided by 2. 64 looks like. Okay, now we're looking at a problem very similar to the ones that we've been doing. I got to get that 64 into a base 2. 2 is prime. So I've got to take 64. I'm going to start dividing it by 2. So that'd be 2 and 32, which 32 is divisible by 2. That's 2 and 16. 16 is divisible by 2. That's 2 and 8. And 8 is divisible by 2. That's 2 and 4. 4 is divisible by 2. It's just 2 and 2. All right, so that's 1, 2, 3, 4, 5, 6 2's. So 64, instead of showing it as 64, I'm going to show it as 2 to the power of, I lost count there, it's 6. And this would equal base 2 to the power of n. There we go. The bases match. And we won't have to do any solving here at the end. We just got to rewrite this now without any bases, because this is telling us that the exponents, if I can get these to match, and that I could, if I made this n a 6, then I should get a true statement. So now let's go back. This means if you replace this n with the 6 in this side, so 2 times 2 to the power of 6 plus 31, you will get 159 out of that. It's our solution. This one starts out as a logarithm, right? But I hope we noticed in the beginning here, and this is the same with exponents, the same with logarithms. The base of 3 is exactly the same. So even though it's log base 3 of this product, 3x minus 1, and then log base 3 of the product, 2x plus 6, again, if I could just get whatever's in these parentheses here, the products, to match, then it doesn't matter. Because, and that's specifically because the bases already match. So I can ignore the logarithm and the base. So in other words, 3x minus 1 equals 2x plus 6. And now I've got an equation to solve. And since we enjoy it so much, well, hopefully we enjoyed this part. So I got my x on the right, so the negative 1, I'm going to have to zero that out. So plus 1 on, again, it's a principle of equality, so it's got to go on both sides. That's going to zero that out. And then the 2x is on the number side of things. I got to zero that out because it's an x term. So minus 2x's on both sides. Again, that's to zero that out. So what do I get? 3x's minus 2x's is 1x's. And this equals, we already zeroed out the x term, but 6 plus 1, 7. And the coefficient is already 1. So this is done. Now, again, if you knew how to type this into the calculator, you could try it. Log base 3 to the, of 3 times 7 minus 1, which is 20? Yeah, it's 20. And then log base 3 of 2 times 7 plus 6 is log base 3 of, you'll never believe it, but it's 20. So you get log base 3 of 20 equals log base 3 of 20. And yeah, that should match no matter what. So to solve this one, we want to isolate the x first. So let's make that a little bigger. And right now, it's kind of like e to the x is part of its own term, right? Because the exponent has to stay with the base. but it has a coefficient of 17, and then we got the minus 8. We need to get rid of that stuff. And the first thing we're going to do is, like I said, isolate the variable. And I'm talking about the 17e to the power of x. I would like that to be just by itself, so I don't want the minus 8 there. So I'm going to have to add 8 to both sides. So let's add 8 to both sides then. And on the right side then, because the negative 8 plus 8 is 0, 2 plus 8 though, on the right side is 10. And now we'll get rid of that coefficient of 17. So the next principle of equality, we'll get, it's going to make that 17 just really a phantom one. So I'm going to divide it by itself. But if I do it to one side, I got to do it to both sides. Now, this is going to drop the e to the power of x, which remains. But over here, 10 divided by 17, I don't want that decimal. It's going to be pretty nasty. So I'm going to make it 10 over 17 as a fraction. But this right here is base e to the power of x equals 10 over 17. And I definitely won't be able to make the base e any form of, or even close to 10 over 17. So what I'm going to do is I'm going to change this into a logarithm. And since it's a base e function, then I'm going to take the, well, you know, I'll show that extra step first. Okay, so it's going to be first log base e, and this is going to be of the product, which is 10 over 17. And then it would equal the exponent, which is showing as x. Now that we have that, now I will show log base e is actually the natural log of, in this case, 10 over 17, and that should equal x. So I, of course, can't do this in my head. So I'm going to go to my calculator. I type in natural log, ln, 10 over 17, enter, and it gives me the decimal. This is my x value. Mine is showing negative 0.5306282511. So, you know what? I'll go ahead and I'll round that to the fourth decimal place right there, the 6. To the right is a 2, so the 6 stays the same. I'll just write this as negative 0.5306. That should be my x value. Now, if you go back and you were to type in 17 times e to the power of negative 0.5306 minus 8, you're not going to get exactly 2 because we rounded the exponent there, but you should get something pretty close to 2, which is enough for us to say that we have, in fact, found the solution. Here we got 8 times Euler's constant e to the power of x minus 17 equals 17. And so we're going to solve this one for x, right? It's an exponent, so I've got a base e. I don't really care that it's base e, but it's to the power of x. I want to isolate that x, okay? So I don't want that minus 17 with the 8 e to the power of x first, so I'm going to get rid of that. And by get rid of, I mean zero out. So negative 17 plus 17 will zero that out. But if I do it to one side, I'm going to have to do it to the other side. So that does zero out as planned, as we forced it to. And then I can take my 8e to the power of x and drop it. And this now equals 17 plus 17, 34. And this is looking pretty good. But I don't want 8 e's to the power of x. I just want an e, 1 e to the power of x. So next up, kind of like we would with a coefficient, I'm going to make that 8 coefficient a 1. In fact, I'll make it a phantom 1 because 8 divided by 8 is 1. Then I'm left with e to the power of x equals 34 divided by 8. We can simplify this. It's 17/4. And as much fun as that is and was, we're not done. And we probably enjoyed that. I probably enjoyed it more than I should have. But we got to solve this. E is an irrational number. So as much as you want to take 17/4 and make it a base E, I don't know how to do that. Well, could I? Maybe I could. But I don't want to do that, even if I tried to figure it out. Because at this point, I'm going to need a logarithm. Okay? I'm going to change this into a logarithm, which is going to help me to solve it. Here's how, in case you were wondering. I don't know that you wanted to wonder, but here we go. So it's base e, right? So I'm going to change this into a logarithm. It's a log base e. And then I have the product, right? The 17/4. So it's log base e of 17/4. And this is where logarithms, at least from a math nerd stance, comes in pretty handy, because I've got log base e of 17/4 equals the exponent up here, which was showing as x, right? So all of this equals x. So now I have an expression, no variables on the left side of my equation. It just equals the variable, which means I can solve it directly. Well, how do you put this in the calculator? Well, a log base e here, that's a natural log. So I'm going to put my natural log of 17/4. This is very easy to put in the calculator because this equals x. And so that's what we're trying to find. Let's see what it gives us. So the natural log of 17/4, enter. Got an ugly decimal. I got 1.446918,983. It didn't say where to round this, so I'm just going to round it myself. I will round it to the 4th decimal place, because that's kind of what we saw in that last assignment, right? So the 9 is in the 4th decimal place, the 10,000ths to its right is a 1, which is less than 5. So the 9 just stays a 9. So I end up with 1.4469. You may round to a different place value if you'd like, but that's where I rounded, and I feel pretty good about it. Now, the last thing on this is, again, if you were to put this back into the x, it's 1.4469 rather, into the x, you may not get exactly 17 because we rounded this value. It's not exact. So you may get something very, very, very close to 17, but maybe not exactly 17. But the actual natural log there that we had in the beginning, if you were to replace that in for x, then it will work exactly. So this one, base 7 to the power 4x minus 3 equals 43. 43, I believe, is prime. So we can't just say, well, we're going to divide it by 7. Can't do it, because if you did, you'd get some kind of, I think it'd be a pretty ugly decimal, by the way. So that means we may be stuck at this point, but we're not, because of logarithms. What we can do is we can take this base 7 right here, and we can make it the base of a logarithm. So I'm going to make it a log base 7, which is okay. And that's of the product, which it was showing over here is 43. This equals the exponent, which was showing as 4x minus 3. So this is now kind of going back into, what was it, 5.3 and 4? The importance of just being able to change the format into logarithms, because this base and that product, the base of 7, the product of 43, it's ugly, right? We can't, 43 is not a multiple of 7, and so we can't just say divide by 7, get some decimal values, and take it from there. We are trying to solve for x, though, okay? Now, before I solve this, before I put this into the calculator, here's what I'm going to do. I want to just isolate the x and see what we get. So my log base 7 of 43, I'm going to keep it. Some students may choose to evaluate that at this point with the calculator, because that's what we're going to use when we do evaluate it anyways. I'm just going to proceed as though that value were just constant, which it kind of is. So let's use some principles of equality here. Let's get rid of that minus 3, right? We're trying to isolate the x, so let's add 3 to both sides. Now the plus 3 that I'm putting right here, I am purposefully offsetting it from the logarithm, because it's not a like term that I can just simply combine those two. So this means then that I have the log base 7 of 43 plus 3. But this would then equal, right, because we zeroed out the negative 3, this allows me to just drop the 4x. So if you had evaluated this log base 7 of 43, maybe you have a value that you can add to 3, and that would be fine. But again, I'm keeping them separated because I don't want to round and I don't want to write the decimal out, because it should be pretty ugly. The last thing I need to do here is I need to get rid of that 4, or just make it a 1, phantom 1. So I'm gonna divide the right side by 4, but if I do it to one side, I got to do the other side That means I've got to do the whole side by 4. Okay, so this is going to give me a phantom 1x equals, I'm now going to put this into the calculator. Okay, the log though, log base 7 of 43, this goes back to what we saw last time. I'm going to change it, I'm going to use common log, so I'm going to change it into the common log of 43 divided by the common log of the base, which was 7. Okay, so instead of, I can't type this specifically, log base 7 of 43, into my calculator. Some calculators can. We're going to have to type this part in and then the rest of it. So here's what I'm typing into the calculator. First thing I would do is I would push the N over D button because I got a fraction right there, right? That's going to give me a fraction line. But then I've got to push the N over D button again, which is going to give me another fraction line. That's where I put those logs in. And then in that numerator, because I'm still in the numerator, I'm going to put plus 3, and then I'm going to divide that by 4. Okay, so I can make this look exactly like what I have right here, but I've changed this log base 7 of 43 into the same basis so that I can just type this into the calculator. Let's see what we get. Okay, there it is. Like I said, I was expecting a pretty ugly decimal. It did come out pretty ugly. And this one comes out as 1.233218626. I'm going to round this to the, I'll do the 4th decimal place again. So the 2 right there, the one immediately to the right just keeps that a 2. So it's going to be 1.2332 for me, rounded, of course. I found it. Now, try it. You may want to try this. Just go back, do 7 to the power of 4 times 1.2332 minus 3. And you may not get exactly 43 because we rounded, but you should get something fairly close. In fact, we rounded, I guess you'd say down. So you may get like 42.9 or something like that. Something like it.